Good morning and welcome to today's session. Today we are going to discuss Fourier integral representation. In this session we will formally define the Fourier integral representation, Fourier integral representation of odd and even functions, and finally Fourier sine and cosine integral representation. The Fourier integral theorem states that if f of x is an absolutely integrable function, piecewise continuous in every finite interval and has a right hand and left hand derivative at every point, then f of x can be represented as the Fourier integral as f of x equal to integral 0 to infinity a of omega cos omega x plus b of omega sin omega x d omega. In simple words, we can say that this f of x can be written as a continuous sum of cosine and sine terms. Here a of omega and b of omega are known as Fourier coefficients. Our aim is to find out this a omega and b of omega and substitute that in this integral. That's all. So f omega is equal to 1 by pi integral minus infinity to infinity f of nu cos omega nu d nu. Here nu is the dummy variable. B of omega is equal to 1 by pi integral minus infinity to infinity f of nu sin omega nu d nu. The purpose is writing f of x as an integral, and this integral involves two coefficients, and we evaluate these coefficients using this dummy variable nu. That's all. We evaluate this a of omega and b of omega and substitute in this expression. Suppose this function is not continuous at a, then value of this function at a can be found using this formula a of a minus plus a of a plus by 2. That means we take the value left of a plus take the value right of a by 2. That means the value at a is average of values of this function to the left of a and right of a. Next is Fourier sine integral representation. The previous slide we have seen that this f of x is written like this. It contains both cosine and sine. Suppose this function f of x is even. F of x is even, then f of x nu into cos omega nu is even function. So integral minus infinity to infinity even function becomes 2 by pi integral 0 to infinity f of nu cos omega nu d nu. And also when f of x is odd, even f of x is even, f of nu into sin omega nu is odd function. So integral minus infinity to infinity odd function becomes 0. So this b of omega becomes 0. So in this representation b of omega term will be 0. So f of x can be written in this form: integral 0 to infinity a of omega cos omega x, where a of omega is equal to 2 by pi integral minus 0 to not minus infinity to infinity 0 to infinity f of nu cos omega nu d nu. That is called the Fourier cosine representation. Similarly, if the function f of x is an odd function, then odd into even becomes odd. So integral minus infinity to odd becomes 0. That means a of omega is equal to 0. Also this expression becomes f of x equal to integral 0 to infinity b of omega sin omega x. That is called the sine representation, Fourier sine representation. Here b of omega can be evaluated like this: 1 by pi integral minus infinity to infinity odd into odd. So it's again odd. We can take odd f of nu as odd function, sine is odd, so odd into odd is even. Integral minus infinity to infinity even function becomes 2 times integral 0 to infinity even function. So b of omega becomes 2 by pi integral 0 to infinity f of nu sin omega nu d nu. We are stating this as the next theorem. The Fourier sine integral representation of f of x is defined as f of x equal to integral 0 to infinity b of omega sin omega x d omega. That means f of x can be represented as an integral of sine terms only. Then this b of omega can be evaluated by 2 by pi integral 0 to infinity f of nu sin omega nu d nu. So f of x as an integral of sine terms. Similarly, we can define Fourier cosine integral representation. The Fourier cosine integral representation of f of x is integral 0 to infinity a of omega cos omega x d omega. Here it contains only cos terms. Then a of omega, the Fourier coefficient, is equal to 2 by pi integral 0 to infinity f of nu cos omega nu d nu. That means the f of x is written only in terms of cos terms. In Fourier sine integral representation, we express f of x in terms of sine terms. As a first problem, we will find the Fourier integral representation of this function f of x. It has two values, namely 1 when mod x less than 1 and 0 when mod x greater than 1. Using this Fourier integral representation, we are going to evaluate integral 0 to infinity sin x by x dx. The sin x by x is called the sinc function. We evaluate this area of the sinc function, area under the sinc function, using this Fourier integral representation of f of x. First of all, we start with the definition of Fourier integral theorem. F of x equal to integral 0 to infinity a of omega cos omega x plus b of omega sin omega x d omega is the Fourier integral representation. Now we write the formula for a of omega and b of omega. A of omega is equal to 1 by pi integral minus infinity to infinity f of nu cos omega nu d nu. But this f of nu has two values, 1 and 0. So in this integration, it is meaningful with the non-zero values. So f of nu takes a non-zero value. When we go back to definition, f of x takes the 1 when mod x less than 1. Mod x less than 1 means x ranges from minus 1 to 1. So that integral minus infinity to infinity changes to integral minus 1 to 1. Here in this place of f of nu we have 1. So 1 into cos omega nu d nu. So integral cos is sine. Again we apply results of even function. This cos is an even function, so integral minus 1 to 1 cos omega nu d nu can be written as 2 times integral 0 to 1. So 2 times integral 0 to 1 cos omega nu d nu. Then integral of cos is sine omega nu by omega, because we are integrating with respect to nu. Integral of cos is sine, okay. Then we divide this term by derivative of this term with respect to nu. Derivative of omega nu with respect to nu is omega. When we put upper limit and lower limit, we got 2 sin omega by pi omega. So a of nu is 2 sin omega by pi omega. Now we are going to find out b of omega. Then substitute these two coefficients in f of x. B of omega is equal to 1 by pi integral minus infinity to infinity f of nu cos sin omega nu d nu. That is equal to integral minus 1 to 1. Say f of omega is 1. So 1 into f of omega nu d nu. So sin omega is an odd function, so integral minus 1 to 1 odd function equal to 0. So this integral goes to 0. So 1 by pi into 0 is 0. So we got a of omega and b of omega. Now we substitute it in the given representation. F of x equal to integral 0 to infinity a omega cos omega x plus b sin omega x d omega. But unfortunately b of omega is equal to 0, so the plus term involving sin terms goes to 0. So it is only integration from 0 to infinity a of omega cos omega x. Now we rewrite this a omega as 2 sin omega by pi omega that we have evaluated in the previous slide. So the Fourier integral representation of f of x equal to integral 0 to infinity 2 sin omega by pi omega cos omega x d omega. F of x as an integral. Now we are going to find out integral 0 to infinity sin x by x dx. For that we start from the Fourier integral representation. It says that f of x equal to integral 0 to infinity 2 sin omega by pi omega cos omega x d omega. Compare these integrals. Here integral 0 to infinity, here also integral 0 to infinity, but 2 sin omega by pi omega cos omega x d omega. Here integration is with respect to omega, so we can take this 2 by pi outside. So we got integral 0 to infinity sin omega by omega into cos omega x inside the integral symbol. So in this required integral there is no cos term. So we can make this cos term to 1 by putting x equal to 0. Putting a omega equal to 0 is not possible because the integration variable is omega. Here x is a parameter, we can put x equal to 0 here and also left side x equal to 0. So we rearrange the terms. That means we make this right side integral to the left side. So integral 0 to infinity, then this 2 by pi in the left side goes to the right side, that is pi by 2 f of x. And so the integration becomes 0 to infinity sin omega by omega cos omega x d omega. Here the 2 by pi goes to the left side, so 2 pi by 2 into f of x. Now f of x is given as 1 when mod x less than 1, then mod x equal to 1, this gives 1 by 2, because at x equal to 1 this function is not continuous. And so we take the condition in Fourier integral theorem, we take the average of the values just left and right to this mod x equal to 1. Left side is 0, right side is 1. 0 plus 1, 1 by 2. So we got 1 by 2 at mod x equal to 1. So we got pi by 2 into f of x like this. Now to make this cos omega x 1, I put x equal to 0. So the term becomes integral 0 to infinity sine omega by omega into 1 d omega is equal to pi by 2 into f of 0. Now look, mod x less than 1 range contains x equal to 0. So the corresponding f value is 1. So pi by 2 into f of 0 is equal to pi by 2 into 1, that is equal to pi by 2. We have already know the result integral 0 to infinity sine x by x dx equal to pi by 2 from Laplace transform. So the final result is integral 0 to infinity sine x by x dx equal to pi by 2. That means we simply replace the dummy variable omega. In our Fourier integral representation given in terms of the dummy variable omega, we can replace the dummy variable by any variable. Here also x is another dummy variable. Integral 0 to infinity sine x by x dx is equal to pi by 2. Okay. Next, we are going to find the Fourier sine integral representation of f of x equal to e raised to minus kx. This e raised to minus kx is actually in the form of the kernel in Laplace transform. So this sine integral representation and cosine integral representation of this function is called Laplace integrals. So first of all, we write the Fourier sine integral representation formula, that is f of x equal to the sine times only integral 0 to infinity b of omega into sine omega x d omega. Now we write b of omega as 2 by pi integral 0 to infinity f of nu sine omega nu d nu. These are the basic results for sine integral representation. Now we are going to evaluate this b omega. B of omega is equal to 2 by pi integral 0 to infinity f of nu. Here f of x is e raised to minus kx, so f of nu is e raised to minus k nu. That's all. Now we expand we evaluate this integral using the result e raised to ax into sine bx equal to e raised to ax by a square plus b square into a sine omega x minus b cos omega x. We use that result here. So e raised to minus kb here divided by coefficient of nu here minus k, its square is k square, plus coefficient of nu here omega, its square is omega square. So e raised to minus k nu divided by k square plus omega square. Put a big bracket, minus k into sine omega nu as itself, plus omega into integral of sine. Integral of sine is minus, that is why here we have minus here. So omega into cos omega nu. Limit varies from 0 to infinity. We have to put this limit infinity to all the new terms. Here also we have nu. We have to substitute the limit infinity here also. When we put upper limit infinity here, e raised to minus infinity is equal to 0. When we put this infinity inside this bracket, that is sine infinity and cos infinity, mod sine x is always less than or equal to 1, and also mod cos x is less than or equal to 1. So whatever be the value of x, it always lies between minus 1 and 1. So these are bounded case. So 0 into bounded value is again 0. And so when we put upper limit, we got e raised to minus infinity into a bounded value. So e raised to 0. E raised to minus infinity is 0. 0 into a finite quantity 0. That's all. When I put lower limit here, e raised to 0 is 1. Sin 0 is 0. Cos 0 is 1. So omega into 1. But there is a minus. So minus of this minus omega. Minus into minus plus. So we can write 2 omega divided by pi into k square plus omega square. That is the value for b of omega. So b of omega is 2 omega by pi into k square plus omega square. Since it is sine integral representation, we need only b of omega. So f of x can be written as integral 0 to infinity b of omega into sine omega is d omega. We substitute b of omega here, that is 2 omega by pi into k square plus omega square into sine omega x d omega. But this can be written as f of x. Instead of f of x, we can use e raised to minus kx. I take this 2 by pi from the left side integral to the right side, it becomes pi by 2. So this integral can be expressed as pi by 2 into e raised to minus kx. So if our function f of x is this e raised to minus kx an exponential kernel, then its sine integral representation is equal to pi by 2 into that function itself, nothing else. Integral 0 to infinity omega into k square plus omega square sine omega x d omega is equal to pi by 2 e raised to minus kx. Next problem, we are going to find out cosine integral representation of this e raised to minus kx. First of all, we start with Fourier sine integral representation theorem. F of x equal to integral 0 to infinity a of omega cos omega x d omega. But a of omega is 2 by pi integral 0 to infinity f of nu cos omega nu d nu. We have to substitute f of nu here and integrate. F of x is e raised to minus kx, so f of nu is e raised to minus k nu. That's all. 2 by pi integral 0 to infinity e raised to minus k nu cos omega nu d nu. As in the previous case, we use the standard result of integration involving e raised to function and cosine. E raised to minus k nu divided by sum of squares of the coefficient of nu. Here minus k, its square k square. Here omega, its square is omega square. E raised to minus k nu by k square plus omega square into minus k into this cos omega nu itself, minus k into cos omega nu, plus omega into integral of sine, integral of cos is plus sine, so we have plus here. So omega into integral of cos, that is sine omega nu. I put upper limit infinity, so e raised to minus infinity, that is 0 into a finite quantity 0, minus, when I put lower limit here, e raised to 0 is 1, when I put nu is equal to 0, sine 0, that goes to 0, then cos 0 here, that is 1, minus k, so minus k. This minus is upper limit minus, that minus, so minus into minus plus, so 2k divided by pi into k square plus omega square, 1 into plus k, that is 2k, 2 into k divided by pi into k square plus omega square. So f of x can be written as integral 0 to infinity 2k divided by pi into k square plus omega square cos omega x d omega. Now we make the constant 2k by pi outside and rearrange the terms, so we get integral 0 to infinity, here we have 1 because I take 2k outside, cos omega x d omega by k square plus pi square is equal to, this pi becomes up numerator, 2k become in the denominator, pi by 2k into e raised to minus kx. That means the Fourier cosine integral representation of e raised to minus kx is nothing but pi by 2k into that function itself. It is also known as Laplace integral. So next is a problem. You have to find the Fourier integral representation of f of x defined as 0 when x less than 0, 1 by 2 when x equal to 0, and e raised to minus x when x greater than 0. To solve this problem, first of all write Fourier integral representation formula. Then you have to find a of omega and b of omega using this function f of x and substitute it back in Fourier integral representation, that's all. Another problem is find the Fourier integral representation of f of x. It has two values, 2 when mod x less than 1, 0 when mod x greater than 1. Here also it is Fourier integral representation. You should start with Fourier integral representation formula. F of x equal to integral 0 to infinity a of omega cos omega x plus b of omega sin omega x d omega. Then a of omega and b of omega are integrals. We have to evaluate that integrals with a of omega is equal to 1 by pi integral minus infinity to infinity f of nu cos omega nu d nu. Here this function defined with the non-zero values only between the range minus 1 less than x less than 1. So a of omega becomes 1 by pi integral 0 to minus 1 to 1 2 into cos nu d nu. You have to evaluate that. Similarly evaluate b of omega and substitute back in our Fourier integral representation. So the purpose of this lesson is to introduce the Fourier integral representation and practice few problems related to this integral representation. Thank you very much.